very long. What we have a harder time agreeing on in general is what are the patterns that we actually need to be paying attention to? And a lot of it involves people, right? So we heard in this last talk that it's not just the physical infrastructure, but it's the people and the processes involved. Most of the resilience in our infrastructure systems comes from the people who are constantly adapting. And they're constantly adapting, not only things go bad, but they're actually adapting on a day-to-day basis to keep things running in the first place. So focusing just on what happens when there's, some major disruptive event is sort of not enough. So I want to end just kind of with a provocation, right? Which is that we're never going to have complete knowledge of these systems, right? These systems and their dependencies are always changing, always evolving. Better planning and forecasting isn't going to get around this. AI ML is not going to get around this for us. We are going to be surprised. Now, for those of you who are early in their careers and trying to figure out, what I'll call business as usual in this research space can make for a very productive career. Right? You can get your degree, you can get promoted, you can get tenure, you can be successful. But my fear is that business as usual isn't actually going to change anything in terms of these large scale disruptive events that we continue to experience. We need some kind of Act 3 that I think goes beyond modeling and simulation, and we need to figure out what that's going to be. So I think we need some new kind of architecture for our mission critical systems. Something that goes beyond traditional optimization and design. And as an operations researcher, right, OR is as guilty as anybody for, faster, better, cheaper, efficient, and brittle systems. So what I liked in hearing Greg Pullen yesterday talk about optimizing for effectiveness, not for efficiency, right? But in the end, we need to figure out other ways of trying to get around this. And I think this notion of adaptive capacity could be part of it. The other thing that I'll maybe just mention and emphasize is that we talk about resilience as about handling challenge. But there's another side of it, which is seeking opportunity. The same processes at work in adaptation are the things that allow you to take advantage of opportunities to do things. And those are the things that actually grow and change systems. So there's been, a discussion that says, oh, it's really hard to sell resilience. And I think that's because it's typically sold in the way that risk is sold, right? We need to spend something in order to avoid some potential loss in the future that we might or might not realize. And that's a hard thing to do when folks have limited resources and they're very focused on the here and now. Investment in things that allow you to grow and change and actually become more responsive to opportunities, that does sell. And so I think there are opportunities in that. So I think that, that's not to say we shouldn't be doing emergency management, right? Of course, we need to do these things. I just think that this space could be much bigger and different if we take it in a different direction. Okay, those are my comments. I'm really interested in reactions.
Thank you so much. One second, before we go to the questions, could you please go back to slide 22? Just let it be there, because our next set of speakers will talk about AI. So
yeah,
let it be there.
Okay.
And then please go ahead. Who did you say first?
Okay. Here.
Sure.
Yeah. Here.
Go ahead.
Yeah, a very quick question.
Yeah.
When you do not know how a system works, ab initio from a theory that works really well, which we do in things like particle physics, but not in operational systems. How would you ever work without data and machine learning? You said machine learning cannot help to take you to the Act 3.
I'm not saying, no, it's not. I'm not saying it can't help. I'm saying it's not going to not going to solve the problem. It's not going to close the gap, right? So here's an example. So all of the big cloud-based services that we now use and rely on. There's been a dramatic change in the last 15 years in terms of how those systems are designed and deployed. It used to be that you had people who were developers and they would write the code, and then they would take the code and they would hand it to people who would deploy it, right? That's been blurred for the last 15 years, where we now have this continued DevOps kind of thing where people are writing and deploying code into production, you know, tens, hundreds of times per day. And so that has some real implications for these systems. In particular, there is no test environment that reflects what real production traffic actually sees. Right? There is no way of testing it other than to deploy it, right? So they devise strategies in and around how to do this, but they actually don't know all the dependencies, even within, you know, a single provider, right? Much less you have software services that are dependent on other vendors, other kinds of things. So what are some of the techniques that they've developed? They've developed something, it's called chaos engineering, where they deliberately inject small faults into the system to see how the system is going to respond. Essentially, they are experimenting on their own system to develop confidence, both in the way the software is written and the teams who are going to respond to do it. And of course, they try to do this in ways that, you know, minimize any potential large scale issues, right? So I think we're in a situation, it's not that we don't know anything, it's that we don't know everything, right? And so there's somewhere in between. You know, our physical infrastructures, it is not at all uncommon, and particularly on military installations, like they don't know where the underground pipes all are, right? They don't know where the valves are. They actually don't know. Right? And so there's a certain amount of experimentation that one, I think, needs to do to kind of discover what's there and how it's going to behave. So it's not that these other things aren't useful, it's that they're not complete. My response to that question is a good question.
Thank you.
Thank you, Mangshu. And
Yeah, Dave, I think it's a very well thought and timely presentation that you made. And I just stuck in your first bullet that probably we never have a complete knowledge of the system. I think it's very true. And this is exactly the same thing I was discussing with Julie in the morning, because, you know, I've been working with the, Texas coast for quite a long time. And every time we develop a new study, right? Because, you know, we try to understand the hazard and come up with a solution, right? Solution could be like, you know, design something to protect the infrastructures. And every time we come up with the new numbers, it's to me, it's like, you know, when I teach my, you know, kid about the addition subtractions, right? Every time we come up with a new number, right? So that's what's happening there. Because if you think about the Harvey, right? Hurricane Harvey was one extreme event. And because of that, the NOAA Atlas 14 came. Now we're coming to the 15, because you have one more point into your extrema that change your statistics, right? So that's why we are keeping, like, you know, probably getting increasing number of hazards, you know, taking all these new surprises, right? So my thought process is, you know, take the adaptive design, because you cannot afford to build higher, right? To imagine for the next extreme surprise. But if we can come up with like adaptive design so that, you know, if something happen, we can actually build upon that one, that could be probably, I mean, more realistic engineering solution that I can think.
Yeah, thank you for that comment. I have two responses to that. One is this first bullet is like there was a lot of soul searching for me that came to that, right? Because so much of my career has been about let's build bigger models, more sophisticated models. Let's get the data. Yes, we can kind of do it, right? And that's just, you know, as engineers, that's kind of what we're trained to do. And if you realize that you really can't do this, then it sort of, makes you think a little bit about what what you're going to do. I think that one of the other thing is, I think that we need think about adaptive models. And what I mean by that is, so, operations researcher, I've come in, I've got my model, I've done my scenario analysis or whatever it is. And you tell me, well, things have changed. You do. There are two responses. Like one, I'll rerun the model, right? Or I'll build a new model, right? Those are the two, responses. So I don't even know what this would mean in terms of an adaptive model. Maybe this is where AI and ML can help us, right, in some way. But that's kind of very much what's on my mind and what I'm thinking about. Okay, there was
On that happy note, we'll come to you just in a minute, but I mean, you can ask the questions, but Osama has to leave at 1:40.
Okay.
So we can come back to the questions. Please hold on a little. And AI is not enough. Osama, you want to respond to that? Osama,
it's not enough. It's not enough.
not enough, yes.
AI is never enough.
Yes. But I think AI can help.
That's a great topic, actually, that we
And
can.
we'll come back to these
Yeah,
questions.
that's I hate to interrupt that
No, please go ahead.
discussion because it's actually very interesting. How do you deal with the unexpected events and the black swans or what have you?
While he's setting up, there was one thing I just comment I wanted to make that he said, you continue to do what everybody is doing and you'll be successful. Versus it will not change anything. So I just wanted to read this comment from Steve Jobs that many of you may have heard to the Pepsi president, John Scully. Do you want to sell sugar water for the rest of your life or do you want to come with me and change the world? The question here is altered a little bit. Do you want to be successful in your life or do you want to change stuff?
They're not mutually exclusive.
After he said that, don't forget that he had to spend a lot of energy firing him out.
Later, yes, that's right. That is true.
Yeah.
He said?
What's the presentation? Presentation over there?
Yeah.
Oh, okay. Fine. Right. All right.
Someone.
All right, so I'm gonna talk very quickly, although I'm much more interested in the discussion topic than in my talk, honestly. So my job is here to, I want to give you a quick update here. I'll talk a little bit about AI and some of the more exciting features. But maybe since it's on my mind, my response will be, look, nobody can predict unknown situations, and models, especially large language models or generative models, are horrible at responding on anything they haven't seen in the past. So definitely that's not the path to address them. And I'll talk about that some. But I do think that the one thing you can do when an unexpected event happens is figure out how to react to it. Reacting to it faster and figuring out the right actions amongst a whole bunch of actions that you could do. That's where I think the technology can help a lot. That's what you can kind of port from event to event potentially and learn from data and learn from analyzing large systems. But would love to discuss because it's a great topic. All right, what's happening here? I think there was a slide before this one, but okay. So you guys all know about AI and you know about the 3 waves of AI and you all, of course, know about generative AI, which is taking everybody's imagination for some good reasons. So the summary here is AI, subset of it is machine learning, subset of that is generative models. And I usually like to use this chart as a reminder to us all. If you were to plot, and this is highly approximate, by application, by use, right? Most applied stuff is really supervised learning, what's called predictive ML sometimes. That's where the class label is given. You know what you're predicting, and you're just trying to do some fancy form of regression or another. Unsupervised learning, where you don't have the labels and you're trying to discover groupings in the data, is also fairly useful in kind of real applications out there. Gen AI, we don't know yet. Right? It's not getting a lot of applications, but it's getting a lot of fascination and people kind of wondering how the heck does it generate all this stuff. My personal theory is for language. Language is a lot easier problem than we think it is. There's a lot of degrees of freedom and flexibility. Same when you generate an image or what have you from a bunch of training images. And things get really hard when you have to be precise, when your answer really matters in a given situation. And then you have a whole bunch of, I use just reinforcement learning here, but there's a whole bunch of techniques in machine learning that haven't seen any real applications in real life that are significant. And there's a slew of them. I could draw a whole bunch of dots here. Now, the two themes that are typically lost are data is very essential. And I can't stress this enough, right? For you, you know, machine learning doesn't know anything about the world other than the data you feed it. And because capturing of events, outcomes, and context is extremely important, but very, very hard. Most organizations don't know how to do this. Most of the time, you don't capture most of the data, especially the unstructured data. We are horrible at managing unstructured data. And when we capture data, we think about the consumers being humans. So we're all about aggregating and charting and all of that. Exactly the opposite of what learning algorithms need to build any kind of useful model. Human intervention is also essential. That's a point which is really ignored by all the, but it's not mentioned by all the big AI companies, but it is done a lot. It is done a lot in Google search engine and MLR. It is done a lot by OpenAI. It is done a lot by Amazon. Armies of people who are providing continuous feedback, continuous correction. And without it, these models wouldn't even perform anywhere near what you see. And that usually kind of always gets me upset that people think. Is there a question?
Well, I was just gonna make a comment that that's true in general for all these critical digital services. Like just even the, having the infrastructure run, having the web services run, everything else. There are small armies of people who are constantly tending to the software and making slight adjustments. And if that were to stop, all these services within a day or two, I think would stop functioning.
Exactly. I agree with that, except you said the keyword, small armies of people. Here, it's actually large armies of people. So you may not know this, but Google search engine, about 20 to 25,000 people work as search editorial team. What does that mean? You're just a generalist. You're using your common sense and you're looking at queries and you're saying move up, move down, irrelevant, etc. And this is done every day, multiple times a day over the past 20 years. Okay. I had to deal with this because we had to build our own teams to do that at Yahoo when I was there. So what is experiential AI? For us, it's AI, effectively AI with a human in the loop. Not only do we think human intervention is a must, but we actually think it's a great opportunity to capture a lot of knowledge. Otherwise, we would uncapture. So those armies doing stuff, whether small or big, are very useful. There's many articles now about ChatGPT having humans in the loop. And in fact, after you do the training and you spend a lot of electricity training I should say, we know a lot about GPT-3 because that was 2020 and it was the last time OpenAI was open. After 2020, they completely closed up. We know that to train the 175 billion weights in GPT-3 on just 1 terabyte of data, a highly curated, highly selected, highly balanced data set, not the whole web. Don't believe it when they say it consumes all data on the web. They tried that, didn't work. That training takes about $3 million of electricity just to converge once. Right? And of course, you do need to do it multiple times. And that's for the 175 billion model. GPT 3.5, we think is about $500 billion. GPT-4, we think is between 1.3 and 1.7 trillion. My personal number is, I think every time you hit train button, GPT-4, it's about a $15 million election. And trust me, none of these sessions ever go to completion. You have to repeat them and rerun them. But after you do that, you need these people to come in, do a lot of fine tuning. They call it fine tuning is a technical term for it. It's a lot of human feedback. So you all know what it is. I like the term stochastic parrots, which is due to a bunch of people who got fired out of Google. But it's a very descriptive term because these things do not understand what they say. They're stochastic because there is a degree of randomness. Why did they capture our attention? Because they went from 0 to 100 million in 2 months instead of 70 months, which is an achievement, by the way. There's many charts now. I try to keep updating this. I updated it over the first time that it got shared by Professor Byron Wallace. But what's interesting about it is most of the stuff is actually open source, which means you can kind of build your own stuff. And I'm a big fan of Llama 2 now. I haven't played with Llama 3, it just came out. But I like them because not only is it a free license to use for academic and research purposes, you can also use it for free for commercial purposes. And the fine print is as long as your business is less than $1 billion of revenue. Summary. Now, the thing that's interesting about this is the economic impact, right? So this hits the knowledge economy right in the kind of forehead. We have created an economy that is filled with a lot of repetitive robotic tasks. And if you ask what is the size of this economy, for a country like the US, it's a little over 50%. So even if the speed ups were not to be 15 to 80%, even if it's a 1% speed up, you can't ignore it. It's 1% of half the economy. And the US economy is substantial. Human in the loop is essential, of course. You need to check the output. You need to modify and edit it. You need to approve it. And that's a big deal. And that's where people get in trouble because they kind of sleep at the wheel and start trusting this thing. And this thing can go crazy in strange ways. Google calls it hallucination. We like to call it mixed errors. Will AI replace my job? I always repeat this in my talks. The answer is no. AI will not replace your job. A human using AI will replace your job if you're not. That's really the key theme here is we got to figure out how to use this in our research, in our education, in our daily lives, etc. So bottom line is not very scientifically interesting. I'll touch on one of the scientifically interesting problems. We know this in statistics, right? If you have a lot of parameters, right, you can memorize the data if you're testing on the training set. But we know that as you increase the number of parameters, you start doing worse. Why? Well, it's statistical overfit in statistics, right? And in fact, there's some theorems that actually say it should do worse, right? Except for one thing that's really weird. You go out here to the millions, billions, and hundreds of billions, somehow it starts performing better. Now, no one understands why. There are hypotheses, there are attempts to explain, but nobody really understands why. So that's a very interesting, PhD topic, if you like. Many technical challenges here. I want to talk about what we're doing at the Institute and how they map to this in a couple of minutes, and then kind of take questions. So people are trying to understand the black box and what works inside it. Actually, David Bao and Byron Wallace and a team are doing some, they just got a huge funding grant to kind of examine what's inside the black box. What's the right size model? Nobody knows. One of the areas we're looking at it is, can you actually incorporate domain knowledge with these things and not have them be purely driven by data? And we spend a lot of time working on responsible AI. And then we had to do a whole, what is responsible AI for generative models? And what does that mean? Because that's a whole other layer of complexity beyond a kind of classic AI. Want to advance? Okay, maybe it does. Okay. So the Institute, we started in early 2021 with good funding by the university and a couple of large parts of large donor grants. The theme is, can we actually leverage AI with the human interaction, with the intervention, and kind of deliver solutions that are grounded in some real problems out there. So part of the, you'll hear from Jennifer next. You've heard a lot from Arup, I'm sure. But what we have is some basic research areas, as well as some focus areas of application. These are being AI in life sciences, AI in health, and AI forecast, which Arup leads. We have the responsible AI practice because we're trying to figure out what we're doing. And we have the AI Solutions Hub, where we basically try to solve real problems to figure out what's going on. In core AI, I said responsible AI. I'll talk for one slide on hybrid language models, because that's an area we're looking into and investing in. But we do have these focus areas where we kind of focus by domain also, where AI can help. So with that, the AI Solutions Hub was designed to basically go and bring problems and work on solving them. The hope is that we can figure out what the research agenda based on the applications that we're trying to solve and where things fail. Then use it also, which is a very nice side effect for Northeastern, as a way to expose our students and our co-ops to what does it take to really do real projects in the real world under real constraints. How do you deal with it when 1/3 of the data is missing and half of what's there is wrong? Which is not what you study in a classroom. And it's hard to study that stuff in a classroom. You need to kind of have the real constraints of a real business and so forth. So with that, large language models. Right? The typical approach in industry or out there in companies is very wide scope. The bigger the model, the better. The more parameters, the better the model, and they flex their muscles and all of this stuff with the sizes of these parameters. Extremely expensive to train, extremely expensive to revise, very mysterious in their properties and their behavior, does something, we don't know why. I don't know, 2 weeks ago, was it? That ChatGPT just went nuts for a night. Just started giving weird answers that nobody understood why. Tesla, right? Was it a week ago where it kind of suddenly out of the blue accelerated and, killed a motorcyclist and hit a bunch of people and cars. The modality is ask me about anything and use any language you like to ask me. Right? But why do I need a model that speaks 60 languages at the same time and pay the cost of making sure it's trained on 60 languages or 80 languages or what have you? They all need the raw data, of course. Our hybrid language models, the idea is to have narrower models, very specific to certain domains, so that the modality is ask me only about X, right? Because I don't know anything outside that, and in a very specific language. Now, that gives you a much smaller model, easy to revise. Some of them you can run on your laptop or train on your laptop even. Much more stable, so the likelihood that you'll go nuts or hallucinate, according to Google, is a lot lower. And you can use prior knowledge. Now, that box there is very, that's a new area of research. Nobody knows, how do I make that additional knowledge usable? So in a large language model, you're basically using a document graph and training up the model. In these hybrid models, you're actually saying, well, what if I have a knowledge graph or a citation graph or a social graph? A lot of the stuff published by Ken Church is on the citation graph, showing how you can do a better semantic scholar, for example. If you add the citation graph, instead of having to rediscover it from data, often erroneously, right? ChatGPT, if you ask it for a reference, this is a well-known symptom. It will make up a reference. It will actually make it up. It looks very nice in format. We put the authors there, Arup worked with me on some topic that we don't know about, and it gives you the year and the conference. It's basically trying to recall what a reference is. It's not good at these precise things. But why would I want to reinvent that? Why would I rediscover it if I have it? I don't think I wrote a paper without it. So it won't appear in that graph. But hopefully that will change that. So the hybrid language model, can you use this? The graph in addition to these other knowledge sources that you have, and how do you work out the math and the algorithms so that you can leverage what's available to you along with the document graph. And you generate these kind of smaller, narrower models, and you may have multiple models working together on different aspects of a problem. We think that's the future. By the way, that's a lot cheaper. I don't have time to cover a case study on it, but I do have a case study on it here if you want. That is why we're taking the experiential AI, because we think pragmatically these things can't run on their own. There's a lot of questions to be answered. I'm going to skip this because we don't have time for a case study here. I want to leave some time for the questions, but it's basically showing you could do some of the really good work that was done there, probably 1,000 times cheaper or less, by utilizing smaller models and have more stable outcome. So with that, I'm just going to summarize and finish here. That's probably good enough. We have time for questions, and I would love to go through
Things just as we start off. So I'll just make two comments and then ask two questions. I mean, one question, but to both of you. The comments are when in the early days when I was here, I started teaching these two courses, statistics, probability and engineering economy. And that was undergraduate, and time series and spatial statistics, and that was graduate. And someone somewhere, I don't remember, asked me, I wanted to study civil engineering or environmental or whatever. Why do I need to do so much computer? So I gave a cheeky reply. I still knew that as a professor. So I said, okay, so you didn't study electrical either. Next time in the class, don't bring your calculator. But to your point about the AI plus human might actually replace the human, not just, not just AI replacing human. And the other thing is, yes, I'd like to take you up on that offer. Pooja, who doesn't look too happy right now, will go to lunch soon. But no, this is for all of you. So we are doing this work, and we have talked about a little bit with NASA. Pooja and August just stepped out. So Pooja from the hydrology side, she's leading it. August from the computer science side, funded by NASA, working with Tennessee Valley Authority, basically looking at generative AI to improve precipitation outcast for flood forecasting. But everything that these generative model generates, Pooja then talks with somebody called Michael and Nathan, and they said, can this be improved a little bit? So maybe that's the angle here. Now, so we'll talk about that. Question for both of you is, so these things, AI, double descent, mysterious models, surprise, is mystery the answer to surprise?
Well, I mean, actually,
And I'll leave it
I
at
don't know if you were here yesterday, but I think everything you said is actually fully consistent with what I was arguing. Yesterday talked about two different kinds of surprise: situational surprise, where essentially your model, you understand your model is correct, but you don't have the parameters necessarily correct. So this is like rare events kinds of things. AI, kind of feedback loop is great for that kind of thing, but there's another kind of surprise, cognitive scientists called fundamental surprise. You have to reframe the problem, reframe the model, right? And that's where I think the teaming part, because humans can do that right now. The algorithms, right? And so,
the algorithms that attempt to mimic or approximate how humans do it, you're absolutely right. They can't do this kind of reframing. They can't do this meta reasoning, and knowledge transfer is very hard for them. However, there is something promising, I have to admit, right? I hate the mystery stuff, but sometimes the mystery has its advantages. A lot of these models, the large language model space, they seem to exhibit an ability to generalize in a strange way, probably related to this over-parameterization somehow. They seem to kind of port skills across different problems. So something that's helping you, working with you, that may have a whole other approach to modeling the world, could actually, that combination, I think, can be more robust to these sudden changes that are unexpected, right? Humans probably have the strength of eventually figuring out what's the right reframing. These algorithms could have the advantage of having some suggestions where a human is completely like shocked by the event, for example.
Thank you. Any other questions? And Pooja and August just stepped in. If you can please identify yourselves. Yes, so we will follow up with you some on that other problem, writing that paper, human AI precipitation nowcasting. But questions, any other questions? There was one.
Yeah, Roop, this is Satish.
Okay. Satish, please go ahead.
Oh yeah, so thanks for presenting it. Just a quick note, because if you're looking at humans in general, if you're looking at the civilian side modeling, it's more of an open world assumption, right? You have a lot more possible parameters, a lot more areas that could go. So the hybrid one is of interest because it's very similar to the thinking of DoD, which is because if you're doing mission engineering, which a lot of the planners do, mission planners do, it's a very constrained vocabulary. You're looking at very constrained vocabulary. The world is lot less kind of what do you call open in terms of when it comes to the doctrine. So any take on that one? Because we have been working on mission assurance, looking at for some time. We're trying to look at free text and things like that to look at emerging processes, process models, business process optimization kind of angle. So just a quick note on that. So if you have anything to elaborate on that, that'd be nice.
I think, and I agree with what you said, and I think actually somehow, unfortunately, the deep learning and the generative AI community kind of went off the deep end in this bigger is better and more general, and are kind of missing the boat, in my opinion, on the power of saying, well, if I narrow my domain and I narrow my scope, not only do I save energy and gain a lot more stability, but I can actually have models that can be dealt with and adjusted and models that are more stable. So I think it's basically harnessing all that extra computation to actually focus on a certain area. And I think, you know, I have a different talk here of the 7 secrets of making AI work. Secret number 1 is you have to make your problem as narrow as possible, and the narrower, the better. And this is what kind of gets missed. Because people want to, I mean, we'd like to figure out how to do this, you know, AGI, the artificial general intelligence, which I believe not in my lifetime will we see it happen, at least not with the current approaches that we're taking to it. It needs something completely different than autocomplete on steroids to get us there. That's, you know, that I think is a more, what you're saying is definitely a much more pragmatic approach. It's like, limit the scope. You don't need to know all the languages. You don't need to know all the variety of all kind of human knowledge and prior written things. But for that one narrow field, one narrow scope, you should know as much as possible and leverage that.
Interesting. Yesterday, Leonardo was talking about homotheos, humanity, apotheosis, humanity reaching the God stage. So that AGI is AI reaching the God state, right? AI deals, but who knows when it'll happen. Hopefully, I don't know if it's a good thing or a bad thing, but anybody else, any other questions? So you and then you. Arijit and then.
So my question overlaps with what both of you all said. Since you mentioned about reinforcement learning and it being in theory and not applicable at a lot of stages, but it is an algorithm or kind of algorithms which can deal with adaptive learning, right? And can help us solve problem instead of just using the traditional supervised learning models we have. What is your take on that?
Oh yeah, my statement was there's nothing against reinforcement learning. And in my training, I mean, I spent 2 years of my life working on genetic algorithms. Did I ever use them in real life? No. Did I spend, you know, sleepless nights working and proving and understanding and disproving some lemmas and all of that? Yes. But and I love this stuff. And, you know, John Holland was on my PhD committee. He was an amazing teacher and professor, and he had amazing thoughts. So I mean, those are all very promising directions. All I was saying was, in reality,
Yeah.
pragmatically, are they seeing applications
Yes.
in kind of industry, in the field? Not yet. But
So
yeah, I mean, reinforcement learning is, you know, fundamentally nothing wrong with it. If you like reinforcement learning, I actually recommend read the one-page memo by Sutton called The Bitter Lesson.
August,
Look it up.
please send it to all of us.
And then read the reply by Rodney Brooks at MIT called The Better Lesson. So those two one-pagers are worth reading if you like reinforcement learning.
Thank you.
So Usama, it's 1:40. I know you have to leave. We had some other questions from our lab. What we'll do is Pooja and August will compile those. If it's okay with you, I'm sort of volunteering you. And from AI Forecast and SDS Lab, and we'll send it. That we can always have. We'd love to have you in general at some point talking to a lab, but
Yeah, and happy to get more involved.
yeah, some more detailed technical stuff. But as of now, thank you, Usama. I know you have to leave.
Thank you, everyone.
Do is, we'll not let Jennifer stand between you and lunch, but we'll have Jennifer, no, we'll have you. We'll have Jennifer. I vote for having Jennifer as the keynote luncheon speaker. We just decided that.
It just means no one pays attention.
Have lunch, if you will, if you are, have lunch. And then she can, yeah, and then she can have her, you know, we can.
Wait for
She will be hungry, I guess.
so the last one.
She's not eating, I guess, right?
I'm eating after.
So there's three kinds. So for everyone, there's three kinds. There's turkey, vegetable, and Greek salad. And it's a good to go, so you can just grab a box or two. I would highly encourage two if you'd like.
So Jennifer is going to pick one box, let her pick. And then let pick all, one box each.
Sorry, you go.
Or two.
Catch lunch.
I got it.
Oh, you.
Yeah,
Satish.
Sure, this is a quick question for you. I think just to seed your conversation. Have you guys looked into the NISAR projects from NASA and India?
Just vaguely looked into, I don't recall everything right now, but that term is not unfamiliar.
Yeah, so it's called NASA India SAR. It's what they're doing is mapping the Earth every 12 days. So every point is going to get mapped once every 12 days. So you have a continuous monitoring of environmental things. So you can look at longitudinal impacts of floods and correlated kind of extremes, right? You can kind of do that on the long term. But I think there is data available online, but I think the launch is slated for some time. They are saying at least sometime this summer.
We shall follow up on this. As a proposal default. Just.
So you. I love.
Front of you.
Maybe I will email you.
All right, that shall work.
Those two pages that Usama.
Yes.
Yeah, I got it.
Yes, exactly. And the other thing is that problem that we are just getting, right? So nowcastnet or any narrative model. Somebody like Michael or Nathan,
Yeah.
the PVA and saying, yes, but this change a little bit, some inputs from them. Nowcastnet will not, because that's a generative whatever. What do we need for that? Reinforcement learning model, something else.
Right.
I'm going to use the cubes of. Okay. So I think we should get it. Anyway, we'll not have the time to get that.
You want me to send that to them? That idea?
No.
Muy interesante. Las charlas.
A short paragraph first, not too much yet. Let's see, I
Me
mean,
pareció muy general. Comunicaciones. Muy interesante. Pero todas estuvieron buenísimas. Dinas, ok, estuvo muy chévere.
Yeah, it's okay to do another time, but not so a
Yes.
few days.
Era mucho del. Antes escuchaba, pero.
Oh, you're future.
Yeah. All right.
Sam.
Please take one.
Sam is actually sitting here. Like, I'm
I'm the one that's being strict. It's okay.
the Delhi style.
Because I just.
Yeah, it's all Turkey.
Oh.
Kind of data, yeah. No, but what do they have for the road data? They have like speed.
We have taken our lunches. This is, we have taken our lunches. And let's give our undivided attention to the keynote luncheon speaker, Professor Jennifer Lee, and she's actually going to bring us home. Robin said very nicely. So
Open your chips before she gets started. Open them because they're really, really noisy. Oh, don't say the name. Open your tips.
Yeah, it's so challenging to talk. And after those two talks too. So anyway, I'll wait for the tip.
ready? Open your chips.
Really loud.
All set. Okay, over to Professor Jennifer Lee.
By the way, I enjoyed the sessions and the workshops, so thanks, Arup. And I'm Jennifer D. I'm professor at the Electrical and Computer Engineering Department. I've also joined Applied Methods for College of Computer Science and director of faculty for the Institute for. So before I start, jumping into the work that we've done on climate, I want to give you a bird's eye view of what I do for research. So basically, I work on foundations in machine learning. And, you know, AI and ML can be applied on any data. But for me, I'm passionate about applying or working on AI applied to any way to help society. In particular, I have lots of collaborations in health. My collaborations is Sloan Kettering Cancer Center in New York, working on skin cancer. And then in Brigham and Women's Hospital, working on COPD, which is a lung disease caused by environmental factors such as pollution and also smoking. And then collaborations with a tech center here at Northeastern in collaboration with Puerto Rico, where they look at actually water quality, toxicity, and also product usage of pregnant mothers to see how environmental factors affect health. Although it's not related, but it's also like they were looking at water quality and toxicity level. So in some ways related to some of the things that are talked about here. I started having collaborations also with psychology groups at Northeastern to understand the brain and emotion. And then with eye disease, you saw Kaushik being in engineering. I have collaborations also with Kaushik, where he brought me in to help with the DARPA project to look at and detect devices, to detect devices from radio signals. And then of course, climate with our room. So I was fortunate when Arup joined Northeastern 10 years ago, we started collaborating, and we were lucky that when we submitted a grant to NSF, we got that grant and got us working together. And I'll talk about some of the work from that. So the type of research I do is that I don't like to just develop methods in isolation. So I collaborate with a lot of this multidisciplinary research because I would like to make an impact on the domain, and it's quite rewarding that way where you advance the science, but also then it pushes the state of the art, because as we all know, your work on is applying toolboxes on a lot of these real world problems. It doesn't work, right? So with that, it inspires our group to start thinking about novel ways to advance machine learning as well. And with that, it allowed us to get in my lab, look into, so because we work with domain experts, they don't just trust algorithms, right? Work so well, high accuracy. I work with doctors, a lot of people working on high risk domains. They just don't want to use it without understanding what's going on. So it led our group and team to really think more about interpretable and explainable AI. I've also worked with unsupervised learning for a long time. Part of that because for example, in the long distance problem, they were interested in discovering subtypes. So again, it gets inspired by real world problems. Of course, dimensional reduction, usually put in data, and then now all of those features are going to be important. How do you do it? How do you figure out the best representation of the data? So it allows us to come up with those models. And then when you work with domain experts, you realize that sometimes they don't believe they think they are not the experts themselves as well. So how do you combine inputs from multiple uncertain experts and find that in the right way? And also getting labels are expensive, so it led us to build methods for how do you intelligently select new samples to be labeled or new samples to query from an expert. And I find actually with climate and environmental monitoring, we can leverage also active learning and expand that to do active sensing. So where do I put my sensor next on things where I am uncertain? So it's related to that and can be extended to those kinds of applications as well. A little bit related to that is patient optimization. So one example of patient optimization would be this is actually perfect for like material design. So what is the best components to put together so that it can optimize something where it's difficult to evaluate. It's difficult, it's costly to get that function. You don't know that function, or it's costly to query that function to get a value. So that's what Bayesian optimization is. Of course, when we work with scientific domain, usually it's specialized, as Osama said. In narrow domains, usually you don't have that many data. It's usually small and curated, but yet you have to make a lot of quality prediction. But usually in those domains, people know physics, or in medical, you have rules that the experts built through experience working through their training and also seeing patients. So how can we incorporate domain knowledge into ML models? So we have also done things like that. And I've also worked on anomaly detection. I put it here because I see that a lot of breakpoints, diffusion detection is also important for resilience. More recently, this is interesting, because this might be one of the ways to address adaptive capacity, is that usually when you build ML models, you build it and then you deploy it to the world and hoping that it will do the right things. But you only train one, right? but really in continual learning, so the goal of this field is that after you build the model, somehow as you do more data, maybe new classes occur or new tasks occur. How do you adapt that model to that new thing? Similar to, I think someone on the online asked the question about open world. It's actually related to open world settings too. So how can you adapt to new things that you have not seen? So more recently too, we have a lot of work on continual learning from our lab, that we're interested in having the automated adaptation to new things, but not forgetting the things that you've learned. And of course, working on climate, also start looking into uncertainty quantification, because this is important in any prediction problem. You need to, it's not perfect. There are unknowns that you don't know, and it's good to be able to also capture that in your prediction so that you can prepare for worst case things. And finally, we've also done some work on robustness. So a lot of learning algorithms are deployed, but it's very fragile and brittle. But when you work with applications that's really safety critical, you need to make sure that it's robust. So hopefully start looking at robust methods. Well, I don't have time to talk all of those, so I'll focus on the applications we have on climate. When Arup came to me, I mean, I get excited because it's my chance to help society, and it's a very interesting problem, but it's a very challenging data and a very challenging problem. I find climate is spatiotemporal and non-stationary, teleconnections, nonlinear, and you have to incorporate systems to that. It's not easy to do all of that. Plus, you have to predict. Usually in machine learning, we focus on doing well on average data. But now we have to think about things where you don't have a lot of those examples. And usually it's a one-time event. It's a very rare event. So it's not easy. But it's also very challenging. And it's heterogeneous data. There's so many data that you can use. It's easy to, how do you combine them? And it's lots of data too. It's a lot of data that you have to build models that are scalable. So here, I'll just talk about this. It's really from the work that we have with Arup. And one of the problems that Arup told us that this is very important, which is climate downscaling. So statistical downscaling. So you all know this better than me. So we have global climate models that are dynamical systems, and usually it's coarse scale. So we have them at 100-kilometer scale. How do you downscale it to something at a finer resolution so that decision makers can do something about it? Okay. So I'm going to talk about the work from PJ, who was a Arup student who I co-advised, and of course some of you also and collaborate also with a lot of here. So one of his first work on statistical downscaling was, so during this time, the approach for statistical downscaling was either regression models or or you can do prediction models, ML models for that. One of the things he started thinking about, or BCSD, which was or BCSD. So one way he was thinking was that, well, really, it's kind of related to computer vision, where I want to related to super resolution in computer vision, where I have coarse pixels, and then now I have to have a finer prediction on finer resolution prediction on my images. So that's what he did. So basically, and also the nice thing about thinking about it from, or mapping it to super resolution is that now it leverage also the spatial relationship of the grids that I have in climate. So that's what he did. He converted super resolution CNN to do statistical downscaling. And he did it as a stack way. So starting from 1 degree by 1 degree to 1/2 degree by 1/2 degree, and then stack it again to 1/4, and then stack to 1/8. So that fully get a finer resolution downscaled version of your climate models. So he called it SD and published it in KDD and won a paper award in the applied track. So it was nice that he was able to convert that problem and translated it to climate. Then of course we're in academia, right? So then we transfer the knowledge to the next student who came and joined our group, which was Yumin. And with Yumin, what he did was he wasn't quite satisfied by doing it by pixel, wants to be able to connect exactly the CCM directly to predict a real valued regression at the end. So he did, he came up with YNet. So basically he leveraged an encoder decoder structure and then did some app sampling and then used the model to give his statistical downscale. And I forget, by the way, the clever thing that TJ did was also included elevation maps, because elevation maps were at high resolution and used that as more like a incorporating domain knowledge into that CNN. And Yumin also used that as an auxiliary input to use this YNet. And it gave good prediction downscale results compared to other neural net architectures at that time. And SDN also the traditional statistical downscaling method that works really well in practice. Now the problem with prediction models using neural nets, and when you work on climate, what's important is to also capture the uncertainty of your models. And the thing with deep neural nets is that it's a frequentist method, right? And also it's a very complex structure. So how do you capture uncertainty for a model like that? Luckily, in the ML literature, Yarin came up with a strategy of adding uncertainty into deep neural nets without having to retrain the neural net again and again. What he did was leverage that training a deep neural net uses dropout. And then what he did was map the dropout to show that the dropout mechanism in a deep neural net, it approximates Bayesian neural net through variational inference mechanism. And basically, it led to like so in variational inference, you optimize the lower bound in Bayesian optimization, and it's in the form of the likely scale divergence of your approximation to your posterior with a prior. Now in Bayesian optimization for typical uncertainty quantification of deep neural nets, usually you add a prior, and to be Bayesian, you add a prior on your parameters. Our parameters were the weights of the neural net, so omega. Usually we assume a prior that's normal. And then the other thing too is that the likelihood also typically in Yargal's formulation, he assumes a likelihood that's also normal. But in climate, we experience extremes. Usually the data are extremes and it's skewed class distribution. So what TJ did was, instead of having a likelihood that's in the form of just a Gaussian likelihood, why not treat it as a discrete continuous form so that when there's no precipitation, it has this probability. When there is a precipitation, then it's done in the form of a normal distribution. So he did like a hierarchical structure where P here is the Bernoulli distribution coming from a sigmoid of the embedding from the neural net. So we built this and then also did another version. So also tried two versions. One is with a Gaussian likelihood. The other is using log normal. Because log normal also is better for heavy tail distribution. So with that, we came up with the uncertainty quantification, and it led to better root mean squared error for the discrete continuous log normal versus the traditional uncertainty for the Gaussian, and also versus discrete continuous Gaussian. And then he also checked for calibration of the uncertainty, and it shows that the discrete continuous Gaussian has better calibration on average, but then on the extreme, on the tails, the discrete continuous log normal has better calibration. Now another work that we have with Arup was the Nature Communications paper that's published by Human, and here we studied river flows, and we noticed that these neural nets are able to do good predictions, and we also figure out which part actually affects the prediction on river flows in the Amazon basin. Because what I learned from Arup that in practice, typically just look at this region. And then we're thinking, can we expand and look at the whole world? Are there other regions that actually allows you to predict better the Amazon river flow? So we use this explainable deep learning. It's actually very simple. We just look at the saliency map of deep learning that works well for predicting the river flow, and discovered for predicting the Amazon river flow. Actually, you can it's a bigger region scale, and then on the Congo it was with red as higher saliency. I'll stop here on the climate side, but I want to also mention about things that we've developed in our lab on explainable AI. Explain a little bit possibilities that one can leverage new things that are being developed in the field. Is that really deep neural nets are great for giving us high accuracies, but it's a black box. We don't understand that. So there's a lot of work in our community trying to make it more transparent. You can think of it as like when I'm given a data, one way to make it transparent is to tell me which features for a given sample is the one that I'm using to make the prediction. Now that saliency map is one way to do it, but there are many other ways to do it as well that our community has developed. One is Shapley. Shapley allows you to figure out which features are important for every instance. So for those who are familiar with feature selection. So again, I'm in the field I work in machine learning for 20+ years, so I grow with the community. In the past, when we do feature selection, it's usually global. So I have a model, and it tells you which features are important in my model that are used to make that prediction. In recent in recent papers on explainable AI, the new developments are really, we are also able to and capable to tell you which features are important for every instance. So now it's an instance level feature selection. I can tell you, given this input, which features are the ones that I'm using to make that, causing me to make a prediction of there's going to be a flooding event or not. Okay. So that way it at least unboxes this and help you check whether it's true or not, is making the right decision or not. So it allows you to make it more transparent. So one technique available is the univariate SHAP. So it tells you which features are important. It uses a game theoretic strategy of evaluating feature importance. One thing that we did in our group was extend that to bivariate, where now I can tell you which features are important if some other feature exists. So you get a network and dependency of some sort. So I just want to highlight that that's also available, because a lot of the things this group like networks. So that's, and you can extend it also to higher order. We just didn't do the higher order because it's just computational complexity becomes really high. Another version that we have developed was the saliency map of deep neural nets. One way to do that is to take the gradient to tell you which pixels or which features are important by looking at the gradient. That's one way to do it. If you take the Hessian, you also get interactions. More recently, we've developed a method called smooth Hess. Basically, we developed this because when you use ReLU networks, the Hessian does not exist because ReLUs are going to be piecewise linear. So there's no Hessian. So how do you do it? So we developed a strategy of how do you calculate the Hessian when there is no Hessian in ReLU networks, and we did it using also in an efficient in a way where you can calculate it by doing Monte Carlo sampling of gradients, and also using Stein's lemma to prove that you can do that. Again, you can imagine that I show you the saliency map of the neural net on climbing. I can take the Hessian too, so now you can get directions from there. Another thing with explainers is that a lot of people just come up with these local explainers, but when you work with domain experts, they'll ask you the same question as you're asking, which features are important. Do you trust it? Are those good explanations? So that's why we started looking into formalizing how do you analyze explainers, because explainers really are function approximators of a black box. So we started looking at how do you measure robustness of explainers and how do you analyze that? So we have this recent paper that's gonna be AI stats on that. And we also show that your explainers are more robust because we formalize it. We've shown that it's more robust if your black box or classifier is smooth. The smoother it is, which is basically the more regularized it is, the more smooth. The explanation is also more robust. So that's what we discovered as well. And also, since this group likes uncertainty, similar to us, my students also now looked at, because an explainer is again a function approximator, we also look into uncertainty quantification of that explainer itself. So that's another work that they've done. Now, finally, I want to talk about continual learning, which I mentioned earlier, because a lot of people were asking about how do I adapt models, and it's quite critical, right? Because especially with Gen AI or transformer models, they're now we're building ML that's really large. And basically what's going on is that it's almost like memorizing the whole data. Now, how do I move this to adapt to something, to a new task or a small task? In some way, there's a lot of work in machine learning that look at domain shift, distribution shift, and domain shifts, or transfer learning to allow you to transfer that big giant model to something smaller and fine tune to specific tasks. And there's one work that does prompting to allow you to do that. And my student was working on continual learning, also developed a strategy that's similar. Basically, it automatically learns a prompt to that whatever transformer model you have to now adapt it to a new task. He was able to do that, and it works really well. And you can do that continuously, and did really well. So this is one of his work. He did this while he was at Google as an intern, and it got a lot of hits. But before that, he started this path. So the student I'm talking about is Zifan. He's an amazing student. We started looking at continual learning through our project on the radio frequency one, because the task that was given to us was have 10,000 devices, build a classifier. So we built that, but then we realized that they also want us to deploy that to the field to detect new devices. And some of the devices may not be in the training set. So it made us start thinking about the open world problem. How do you adapt to this training to learn new classes without forgetting what you've learned in the past? So it allowed him to come up with this open world class discovery problem where I have a deep neural net that works really well. And then now we cast it as an open world problem. It's really a semi-supervised open world problem where now can I learn a new embedding in this space or new clusters on new data with also leveraging the embedding or dimensionality latent space representation in my supervised task before that, and combine it to allow me to do well on the new task, but not forget what I've learned from this. So this is what we did, and then now you can iterate this and so on. So we have several versions because again, the student was very creative. We have several ideas. One of the ideas that was cool too is that you learn and then you can expand your neural net for the new task. So first you learn and then you prune it, compress, because when you learn a neural net, there's a lot of redundancy in the weights for very deep networks. So we prune it, and then now when you see the new task, you grow it, and that allow also learning what to share, so on. So this is also another mechanism we've done. And I don't want to bore you with other things. You can look at the papers, but it gives you a peek into like what's possible as well with building adaptive models. And I want to end here and thank the students from our group and my team that work together. And I just want to say that new students I have in my lab.
Questions?
Yes, Sam.
Thank you so much, Jennifer. Really enjoyed learning more about all the lines of work you've been involved in. So I was just curious. I was thinking about the compound extreme sort of theme and the question about data. And yes, we have data for various types of hazards, but maybe in some cases we have data for from a system side, maybe we have lots of data on regular or normal operations, but it's those atypical situations, right, where we have maybe very little or maybe no data at all. So just curious your thoughts on from the AI machine learning sort of lens, Like how successful do you think like these few shot or zero shot learning type approaches, can they help us in sort of situations where we have maybe no data or very little data, possibly out of context data? Just curious about your thoughts there, or maybe there are other sort of, directions in terms of research.
Yeah, I will, yeah, I might, I don't know, I would try. That's what I would usually do, like, so, so, so for one shot, few shot learning, it's sort of like the prompt-based method that we have, so you can learn like a large training from a supervised task from the past. I can imagine we could do something like that. And then I think the prompt-based might work for one shot. It depends on how big you build it. I will give it a try. Another thing I would try would be really an outlier detection problem. I can learn normal. I have lots of data on normal. So learn that well, then see if then I can detect outliers. But now you can be more clever in designing the score for an outlier test. Because you can learn like a really rich representation with it's unsupervised learning. So you can have a deep model, use that embedding, and then figure out whether there's outlier, and there are many ways to explore that space as well for checking outliers. I would try that too. So, and then see which one would work well on the particular setting and data you're working.
So one thing, I'll just hold off on the questions from our lab and AI forecast now, because we have a gracious offer from Jennifer. So please hold those questions, come to them. But since I'll be out for 2 months, starting May 4th, especially since, but even in general, Jennifer has offered that, not yet offered.
Not yet,
Not
but
yet
yeah.
offered, but may
But
offer.
he's very smart.
He offered, she said that every 2 weeks, if we can meet. I said, this is the perfect time to start because I am out. But even if that doesn't work, but let's compile those
Yeah.
questions from our lab and AI forecast, send it to her, let her make up her mind if it is 2 weeks or every 1 month. But you can meet, that'll be great. In any case.
But I would love to work.
Yeah, and in any case, it'll be good for them to talk with your students, et cetera. So maybe every 2 weeks, once every month with you, whatever. Meanwhile, Marta has a question.
Yes.
Very nice talk. Thank you. I found very smart the idea of the prior log normal. I was surprised that the result was not better. That's one question, and I would like to get your insights on that. What can we do? Why it didn't get much better? And the other one is
On the tails though, it was better on the tails.
okay.
The other one was better on the regular. Yeah, so yeah, which was, yeah.
Yeah, so on the tails precipitate.
Yes, yeah, and then what was the input for training and testing on the downscaling of precipitation? You have weather station data, or how do?
No, it was reanalysis data, unfortunately, what we didn't have.
So you have the low resolution data, and then you are downscaling. How to validate?
So we have the reanalysis on the higher resolution one, and then to train it, we subsample.
Okay.
Yeah,
So it
the
was an
tails.
exercise.
Yes,
Yes,
that's
I
an
see.
exercise, yeah. But during tests, you then.
And just to add on to that, in the first deep SD paper, we also used PRISM data, which is basically a problem.
Yeah, that's the reanalysis data. Got it. And to answer the surprise, you can never prepare, right? But I grew up in a conservative culture where you have to prepare the worst. So maybe that's what we can do, prepare the worst case so that we're ready when something happens. And I think we should, because we don't know. There's so many things, right? Maybe for the prediction models to at least give us a few days warning when something may or may not happen. The other thing I was thinking too, I really like the idea of simulations, because simulations allow us to really think about scenarios that may or may not happen. And you can do that also on you can do that just on the computer. It doesn't have to do it in real life. So we can do something. And of course, you can never take into account everything. So
So in our world, meaning the royal we, the broad world,
Yeah.
nat cat models, natural catastrophe models in the insurance market, that's what they do. They would generate 100,000, 200,000 simulations. The issue with simulations is, I think, what Dave was saying, that you don't know what you don't know. So you're still simulating based on some physics or some of the understanding that you think you know, but.
Yeah.
In the interest of time, though, we have, by around 2:45, we have to set up this room for the Air Force. We have a separate presentation to the Air Force independent of this. So very unfortunately, we have to close this discussion, but she is right here. So I mean, in Boston here. For everybody else, please reach out to her.